In this final lecture, we'll take a look at steady uniform flow in an open channel having a constant slope. We will also look at the Chezy and the Manning equation and work numerous examples. In this section, we will consider steady uniform flow in an open channel having a constant slope. Since all open channels have a rough surface, and in order to maintain steady uniform flow in the channel, it is essential that it have a constant slope and a constant cross-section and surface roughness along its length. Although these conditions rarely occur in practice, analysis based on these assumptions is often used to design many types of channels for drainage and irrigation systems. Furthermore, this analysis is sometimes used to approximate the constant flow characteristics of natural channels such as streams and rivers. So in this diagram in the book, he defines some generic properties of shapes you see. He gives the area and perimeter. A is area, P is perimeter. RH is the hydraulic radius. This is the ratio of the area of the flow cross section to the wetted parameter. So in some of the problems, you can come back and look in these diagrams and calculate A and P. For open channel flow, the Reynolds number is generally defined as follows. It's equal to the velocity times hydraulic radius over the viscosity. Practically all open channel flow is turbulent. In fact, nearly all flow occurs at a very high Reynolds numbers. There's two equations we're going to look at in this section. The first one is called the Chezy equation. For a steady uniform flow along a channel of slope S0 and hydraulic radius RH, the speed is given by this following equation, where C is equal to the square root of 8G over F. F is what's known as the friction factor, and depends on the Reynolds number and channel parameters. The coefficient C was originally thought to be constant. However, later experiments show that it depends on the shape of the channel's cross-section and the roughness. So this diagram shows you sort of what we're looking at here. S is the slope is measured in reference to the base level. The second equation we're going to look at is what's known as the Manning equation. So in 1891, Robert Manning established experimental values for C in the Chezy equation by expressing it in terms of the hydraulic radius and a dimensional surface roughness coefficient N. His equation is as follows. Typical values of N given in SI units for some common surfaces conditions are given in table 12.1. And you can see these are a range of values because, you know, it's sort of like friction itself. It really depends on a lot of it falls within this range. So you have to sort of, you know, go by that. You know, typically the problem will give you an absolute number for this, and it'll fall between these values. But if you know, if in the real world you just sort of pick, you can sort of pick values sort of maybe midway in between these values. So the Manning equation is given by the following, is the following equation. Uh, K here is constant based on what units you choose. If you choose SI units or you choose English units, you choose 1 or 1.486. The volumetric flow rate Q of a fluid that flows through a cross-sectional area A is given by Q equals V times A, as we've seen before, where V is the velocity. Since the hydraulic radius is given by the formula RH equals A divided by P, we can rewrite the Manning equation in this more useful form. So for a given slope S0 and surface roughness N, the flow Q will increase if the wetted parameter P decreases, as you can see in this equation. Therefore, we can obtain the maximum Q by minimizing the wetted parameter P. Such a constant cross-section is called the best hydraulic cross-section, since it will both minimize the amount of material needed to construct the channel and maximize the flow. So let's take a look at best hydraulic cross-section. So in this example, let's suppose that the channel has a rectangular cross-section given by width B and the liquid depth Y. Then the area is simply B times Y, and the perimeter is given by 2y plus b. Notice we don't include this top part since there's no, this is just open surface. Thus, for a constant value of a, the relationship between b and y is not as yet known. So we can take a derivative of dp with respect to y and set this equal to 0. And if we do that, we find a is equal to 2y squared, which is obviously b times y, so y is equal to b over 2. So therefore, for a rectangular channel flowing at a depth of y equals b over 2, will require the smallest amount of material used for its construction. Since this design size will also provide the maximum amount of uniform flow, it is the best cross-sectional size for the rectangle. And you can repeat this exact analysis for other shapes. So we look back at the channel, how the channel slope falls in the Manning equation. We can solve the Manning equation for S0. So here's the generic equation for S0 as a function of any q. So at the critical depth, y equals yc, as we've seen before. So the flow rate is given by q is equal to ac times vc. These are both critical values. So vc, we know is the square root of gac over the top width. Therefore, for the critical slope for a channel of any cross section is given by substituting this last equation into the equation for S0 at the top. The result is known as the critical slope, SC. So here, the critical area AC and the hydraulic radius HRHC are determined by setting y equals yc for that section. With this equation, like the depth y, we can compare the actual slope of the channel S0 with its critical slope SC and therefore classify the flow. So if F0 is less than SC, it's subcritical flow. If they're equal, it's critical flow. And if S0 is greater than SC, it's called supercritical flow. And we'll see some of these, this in some of the examples we'll look at later on. So let's look at example 12.8. So this channel is made of finished concrete, and then the bed drops 2 feet in elevation for a horizontal stretch of 1,000 feet. Determine the steady state uniform flow when the depth of the water is 4 feet. Take n to be 0.012. So here shows a little schematic of the flow. You have a 2 feet drop over 1,000 feet. That determines the slope. 6 foot wide, and the water is currently 4 feet deep. So given those, we can determine the hydraulic radius is A over P. So the area is 6 foot times 4 feet. And the perimeter is 4 feet plus 6 feet plus 4 feet. And notice we do not include the top part because that's just open surface. So the hydraulic radius is 1.714 feet. Since this is English units, we're going to choose our K value as 1.486. So we can solve our Manning equation and determine Q. That's the only thing we don't know here. Q is 190 cubic feet per second. And notice on this side, this is Q divided by the area. 4 feet times 6 feet, the flow rate. So let's take a look at example 12.9. The channel consists of an unfinished concrete section and is 0.14, and overflow regions in each of the side contains light brush. So in other words, you have here's your channel, and on this side and this side, there's brush. So it has a different N value. It's 0.050. So if the bottom of the channel has a slope of 0.0015, determine the steady volumetric flow rate when the depth is 2.5 meters as shown. So this shows the depth. It's 1 meter from the rough brush to the surface, and it's a 2.5 meters from the bottom of the channel up to the top. So for an approximate solution, the cross-section can be divided into 3 composite rectangles. So here's one rectangle, here's another rectangle, and here's the third rectangle. The flow through each cross-section is thus the sum of the flows through each composite rectangle. Also notice for the calculation that the wetted parameter does not include the liquid boundary between the rectangles. So in other words, this boundary or that boundary is not included because they are not part of the channel's wall or bed surface. So we can write Q as the sum of each rectangle, of all those rectangle areas, parameters. S0 is the same because the slope is the same, so we can factor that out. That's what we're dealing with in meters. The metric system, our K value is 1. That's where the 1 comes from. So all that's left is the area divided by n times the parameter on each of those. So A1 is the area of the first rectangle, P1 is the perimeter, N1 is the n value for this one. Same thing for area for rectangle 2, and then for rectangle 3. So these are pretty self-defined. So if you look at like A1, for example, it's 5 meters times the depth here is 1 meter, raised to the 5/3 power. N value is given. P1 is just 1 meter plus 5 meters. And again, we don't include this part because it's not really, it's just water there. So we repeat that for each rectangle, for rectangle 2 and rectangle 3. So we calculate the Q value, composite is 20.7 cubic meters per second. Example 12.10. Here we have a triangular flume is used to carry water over a ravine. So it shows a diagram of it. It's made of wood and has a slope of 0.001. If the intended flow is to be 3 cubic meters per second, determine the depth of the flow. Take n to be 0.012. So here we're going to assume a steady, uniform flow of an incompressible fluid. We're going to treat water, obviously, as incompressible. So if y is the depth of the flow, then from figure 12.2, the perimeter is 2 times the square root of 2 times y. So you can kind of follow that. You got this side here is square root of 2y, and you got this side and that side, so you just double it. The area is 2 times 1/2 base times height. The height is y, the base is y, so it's and the twos cancel, so it's just y squared. So for SI units, remember K is 1. We can plug in the area, plug in the S value, which we're given, plug in the N value, plug in the P that we saw for. So we get Y is equal to 1.36 meters. Is the depth that the water would flow at. Last example, 12.11. This channel has a triangular cross-section is made of unfinished concrete. If the flow is 1.5 cubic meters per second, determine the slope that produces the critical flow. Take n to be 0.014. So here shows you maybe a little diagram of a triangular cross-sectional channel. Notice in the diagram here, he's actually given us the slope here. You can use, Pythagoras' theorem where you can calculate this angle here. The tangent of this is 2. It's 2 divided by 1, which is 2. So we can use those to calculate the perimeter and the area. So first of all, let's review a little bit. Back in, I think lecture 2, maybe lecture 1, we looked at the energy equation. So the energy is kinetic plus the potential. If you take the derivative of E with respect to y, set this equal to 0, what you find is that there's a relationship between Q and the critical area. Q squared over G is equal to AC cubed over the B top, in which B top is the length of the top surface here. So using that information, that equation 12.11, We're going to use that in this example. Uh, First of all, you can calculate the area. Uh, you can use the equations. I'll show you how to use the equations at the beginning of this lecture. And this one's kind of simple. You can just kind of calculate it. It's uh, you got two triangles, this triangle here, this triangle, so it's two times the area of one triangle. So it's 1/2 uh, base, which is 1/2 YC times the height, which is YC. So this is 1/2 the base times the height, and you got two triangles. So uh, these cancel, so it's just 1/2 YC squared. The top is just 1/2 YC plus 1/2 YC, which is YC, the distance from here to there. So using that equation 1211, you know what Q is. G, of course, is known. Uh, AC and B top are functions of YC. So you can determine what YC is 1.129 meters, the critical depth. So using that value, B top is YC, which is 1.129 meters. The area is 1/2 times that value. Uh, the perimeter here, uh, down here at the bottom, I'm going to show you how to calculate these in a way. So here you can calculate, he gives this little figure, so you can calculate alpha. Alpha is this angle here, so it's the inverse tangent of 2 divided by 1, which is 2. So that angle alpha here is 63.43. So you can use these equations to find the area and find the perimeter. You can also do that the old sort of this using geometry in a way. Uh, Here you know what, like for example, for the perimeter here, you're trying to find this distance here plus this distance here. So uh, this side is YC, which is 1.129 meters. This is half of YC. So actually you get 1.129 meters squared plus 1/2 of 1.129 meters squared. And then take the square root. So we're really doing the Pythagoras' theorem to find this side here. And of course you got this side and you got the same thing over here, so you have to double it to get the perimeter. So you get the same value, 2.525 meters, whether you use the formulas or you use your trig and geometry to do that. The hydraulic radius is AC over PC. So here, those are just those values divided. So finally, you can calculate the critical slope as plugging in your values here, 0.00680. Therefore, when a channel has a flow of 1.5 cubic meters per second, as stated in the problem, then any slope less than this SC will produce subcritical flow or tranquil flow, and any slope greater than SC will produce supercritical or rapid flow.